Can you guys all hear me? Okay. Is this working today? Okay. Because this room is so big, I want to make sure you guys can hear me. So that's good. Okay, well, so I saw that many of you have already submitted your homework last. Hopefully that it was easy for you to do the homework to submit, right? So as I said before, the score that you got on the homework, whether it's a 3, 5, or 14, or 10, whatever, don't pay attention to that. That's the only indication that you submit your homework. Now, of course, I hope that if you get a 3 or 5 out of 10, you would have redo your problem, because otherwise you have trouble moving on to understand basically the class material and finish your future quizzes and exams. So hopefully that, yes, you did. If you get a low grade, make sure you redo them and you got pretty much correct. At least it doesn't matter whether it's showing on the actual quiz grade. Okay. So we're gonna have a quiz today towards the end of the lecture. So we're probably gonna stop at 6 and have the quiz 15 minutes. Again, if you were missing from the previous classes, the quizzes are gonna be you have to hand in your paper, so you cannot do it on your iPad or tablets. You have to write on paper. If you don't have a paper, I thought I was going to bring some paper, but I forgot. But if you don't have one, borrow one from your friend next door, so that you can write it. Write your name and your student number and write the solutions step by step. Don't give me a paper as saying X and Y, Z solution is 5 amps. You're going to get a 0 on that. Okay. Regardless whether the answer is correct or not, you're going to get a 0. You have to submit your step-by-step work. How you calculate every equation, you have to, don't try to neglect steps. Even if you say, okay, this is easy, because from the figure we see VDS is 5. Don't do that, because I don't know how you get 5. Yeah, you have to write down VD is equal to VD minus VS and blah, blah, blah to get the actual number. Okay, don't just write the answer, write the step. The step is what I grade on. It's not the final answer, okay? Understand? Great. Okay, so for the class overall schedule, like we already spent 2 classes, 2 lectures, one in chapter 5, one in chapter 6. Just to kind of quickly recap what you guys learned in the past. Today and the next Monday, we're gonna do it again in chapter 7. I know chapter 7 is something I already also learned, but we're gonna again review. Otherwise, if we jump to chapter 8, it will be very difficult. So for that same reason, we're gonna have 3 quizzes in a row. So we're gonna have one today, one next Monday, and one next Wednesday. So today's quiz is gonna be on BJTs, MOSFETs. Monday is gonna be on BJTs, and Wednesday is gonna be on chapter 7, like amplifiers in general. But then you're gonna get a break for a little bit, so you can focus on studying. And then we're gonna have quizzes coming out throughout the semester. So that's what we're gonna do. Any questions before I jump into chapter 7? Okay. Well, chapter 7, 2 lectures today and then next Monday. So the slides that I posted online is good for 2 lectures. So we're gonna go half of it today and then other half at the end. And sometimes the slides, especially towards the end, they have some like more difficult problems. So sometimes we don't have time to solve them during the class time, but I'll post them, the solutions or the steps to solve the problems, regardless what we covered or not in the classroom. So make sure that afterwards you can download the slides, the 2 sets of slides. One says clean. The one that says clean, you can download and you can solve them, or you can write notes on them yourself. The other one says noted is basically the one that we like discuss in class, so that you can refresh your knowledge. And also the lecture is recorded and I post them on YouTube. Now, the reason that I post on YouTube because it was easy for me to cut edit it. The original recording has the previous 5-10 minutes recording has nothing. I don't have a way to edit the video, so that's why I posted on YouTube. So, but if you needed to review the lecture, go do it. But if you don't need it, just you don't have to do anything to it. Okay. So today we're gonna go through this chapter 7. So let's dive into it. In chapter 5 and 6, we learn MOSFETs and BJTs. And I told you guys that in this class, what we are mostly interested is the active region. So in MOSFETs, it's called a saturation region. For BJT, it's either called active or linear region. Now, I don't know who in the hell invented this saturation, linear, active, because they're so confusing. If you go to BJT, it's a saturation, that's what we need. But then if you go to, you go to MOSFET, the saturation is what we need for amplifier. But if you go to BJT, saturation is not what we want. It's totally different. So I think the concept for this saturation, linear, and triode is based on the performance of the device. So in BJT, for example, the saturation means the voltage between the collector and the emitter is so small that it was saturated. So so that's why why it's saturated. Sorry, I made a mistake. So it's in the linear region. Well, we're going to go through the amplifier for the BJT. For MOSFET, we need the saturation so that they go to the linear operation. So it's just the definition. So in this case, you compare these two, both are the ones that we need for our application. So this is for the MOSFET in saturation region, and this is the BJT in the linear region or the active region. So for the simplicity in the future, if you're still confused, sometimes you got confused between saturation for MOSFET and active or for BJT, you can think about linear. So they're both in the linear region. So this is what we need in the future, really. So I want to write down just a little bit of here. So in this case, in a MOSFET, you get ID. VDS. So the ID is more or less constant, like this. But in the BJT, comes down like this. And this is sorry, this is wrong. This is this VGS 1, VGS 2, VGS 3, and here's VB 1, VB 2, and VBE 3. It's let me see. And for the saturation in MOSFET to happen, we have two conditions. So let's write down here. So for the MOSFET, for the saturation, the first condition is that VGS has to be larger than VT. If VGS is less than VT, it's going to be in the cutoff region. Possibility. One is in triode, in saturation region. So for the saturation region, the other condition is that VS has to be larger than VO. And VO is defined as VGS minus VT. So this is sometimes also called offset voltage or over voltage, which basically how much VGS is more than VT. So VT is the threshold voltage where the MOSFET start to conduct. When VGS is larger than VT, it's going to conduct and it's going to enter into this region. So if you hold it, because VDS is equal to VD minus VS. And on this side, you have VGS is equal to VG minus VS and then minus VT. So you see here, if I decompose the VDS and VGS, you got VS on both sides. Those can be canceled on both sides. Then certainly you got VD equal, has to be, oh, this has to be large. So it has to be larger than VG minus VT. So if we now move VD to the outside and VT to one side, then we got VG minus VD is less than VT. So this is really the condition for the MOSFET to be a saturation region. Okay, so this is the equation that you really have to kind of remember. So for BJT, it's typically very simple. So first condition is that VBE has to be larger than certain value, and then typically larger than 0.5 in order to be either in saturation region or in the active region. But most of the time, it has to be larger than 0.7 in order to work in a linear region. And then the other condition is that VCE is less than 0.2 volts. So that's the condition for the BJT in active region. Active region. So this is very important to remember. And then if we plot function VD as a function of VGS, like this. Now in this case, if you look at the circuit, you have VGS as the input, and VDS is basically from drain to source, right? So we can write down the equation. First is going to be VD equal to VDD minus ID times RD. So in this case, you can see that if ID is 0, what happens? If ID is 0, VD is VDD. So that's in cutoff, right? If ID is 0, there's no current. So VD is same as VDD. Let's call it this VD. But if ID is so big, most of the voltage would drop on the resistor. So how much would you left at VD? At the most, in the charge region, it will become 0.2 volts. So if you plot it like this, you will see that VD is something like this. So that's kind of the function of VD as a function of ID. And we know that ID can be expressed in saturation is 1/2 K times W over L, VGS minus VT squared. So basically, you can replace that ID in this equation over here, and you got VGS, and you start to plot the same thing, like ID as VGS, the curve is going to be the same, basically similar, very similar. And so that's what you get. Now, why is this important? Because if you look at in this whole circuit, that VD equal to, let's say, come on here, this is VDD. So VDD is the maximum you can get at the output. And 0.2 over here is the minimum output you can get in this circuit. Okay. So okay, here. So this is the actual plot. Is a function of VDD, VD or VDS as a function of VGS. So this is exactly what it simply is. This ID over there is replaced by this equation here, and you can see ID and VGS. This is the square, but they're related. So this is replaced by VGS. And we're going to tell you later on in the middle range, right from here all the way to here. This is the range that we call the active region for MOSFET, which is the saturation area basically. But this is like a cutoff, and this is the triode. And then in the middle range is where we're going to need it for our amplifier application. And then for BJT, we know that in this case we can write VO or we equal to VCE equal to VCC minus IC times RC. So similarly, you can plot VO as a function of VBE. But in this equation, of course, the equation here does not have a VBE. So how do we convert that IC into VBE? Do you remember the equation? What is the relation between IC and VBE? So IC equal to IS times E to the VBE VT. Okay, this VT is not the other VT. For BJT, they use the capital VT, which is the consumer voltage. It's 25 millivolts for silicon. It's something else for some other semiconductor materials. For the MOSFET, that VT is the threshold voltage is 0.5, 1.5, depending on the device material. But this is totally different. So if you replace this IC in that equation by VBE, and you can see if VBE is 0, apparently if VBE is even less than 0.5, what happens? This equation do not exist. Okay, this is only for the BJT to be conductive. So which means that VO is going to be same as VCC in the beginning. And then when you start to increase VBE to about 0.5, it's going to start like this. And at the end, if IC is so big means the circuit, the BJT becomes in the saturation region. That's the maximum current you can get. So then how much voltage do you have at the VCE? Remember? So this is 0.2 volts at the saturation region. So some of you say, okay, you said so big. How big? Well, we can use example. Like example, if VCC is 10 volts, RC is 10K. See how much maximum IC you can get? It's really 10 volts minus 0.2 divided by 10. You get 0.98 milliamp. So when I say the current is so big, I didn't mean it's in amps, tens of amps or whatever, because there's no way you can get that. So the maximum current you can get is just 0.98 milliamps in that circuit. But of course, the minimum current is 0. So the current is between 0 and 0.98 in this particular example. So this is, again, similar to the previous one, we draw this one. This is about 0.5 for the thing to start to conduct. And this is where it's going to go to saturation. The middle region is where we're going to use it as amplifier. So you might hear, you may or may not hear when you learn 330 because they don't talk about it. But here we're going to, in the future, talk a lot about biasing. So what do you mean biasing? I know in real life, biasing means you have just like opinion about something, which is yours. It may not be correct. But in circuits, when we say biasing, we're really saying we're going to set this up at a certain point. So we bias it. Sometimes it's also called DC, like a DC offset. So example would be, okay, let's do it this way. Let's start with example. Let's say you got a DC voltage like this, and you got an AC voltage like this. And let's say the DC is 10 volts, and the AC is, say 1 volt, make it easy. So you have two different voltage sources. So when we connect this to ground, we plot this one. Well, what would you get? So let's plot them. VD is a constant. And then we plot VD, what do we get? Let's say this is like a AC frequency 60 Hertz. It's the sine wave like this, right? So what happens when you have a circuit like this? Let's call it, let's call this one, the small case VD. Let's call this one the larger case VD. So when you plot this one, what would you get? Anybody tell me what do I get for large case VD? I measure voltage across two voltage sources. Yes. It's going to be the AC 1 volt on top of that 10 volts. So basically, you're going to get something like this. Let me use a different color. So that blue line is just saying that's 10 volts. Right? So that, you see what happens that you got here. So this is like a DC offset, and your AC is on top of that. So that's what we're going to be using a lot in the future. We call it DC biasing. So in amplifier circuit, you always need DC biasing. You always need DC biasing. Otherwise, the circuit as amplifier will not work. And in the future, you will see some circuit was a representation, not actual circuit. Why? Well, because we use it to represent amplifier, but it's not actually the actual circuit. So now the next concept that we need, like the previous one, we had example on 2 voltage sources. Then I want to introduce one concept you guys are learning in 210, called superposition. Do you still remember what superposition means? Yes. Yeah. Okay. Yeah, that's right. So when you have a linear circuit, you have multiple sources, whether voltage source or current source. You can solve one by one. And then you can add the solution together to get your final solution. That's called superposition. For voltage source, you will short it. For current source, you'll open it. So when you do the superposition. So we're going to do a simple example here to solve superposition, just to refresh your mind. Again, I'm going to use example of this very simple circuit. So this is going to be 10 volts. This is going to be 1 volt. AC, 10 to, this is a 10K. We call it I, got I. So in this case, you have two voltage source, you have one like resistor. So in superposition, you can do this in solving two circuits. So one circuit is like this. And another circuit will be something like this. And you got this one, let's call it ID. Let's call it ID. So just distinguish between DC and AC and total. So in the top circuit, you will get ID is equal to 10 volts over 10K, gives you 1 milliamps DC. But the second one is AC. So in theory, you can write that voltage source equal to like 1 volt times the sine omega t. So you get I equal to V over R equal to 1 over 10 sine omega t. And that gives you 0.1 sine omega t milliamps. So when you add this together, you will get ID, which is ID equal to ID plus ID, which gives you like this. So initially you got this, which is your ID, and you add on this one. So this is your final ID. You see, you solve them separately, then you add it. You get these two things added together. So this is your final solution. And this VD is right here. So this is called superposition. We're gonna we don't call them out superposition in amplifiers, but we use the principle all the time. So we're gonna really look at how we're gonna do. Let me make sure I got all the notes here. So in the MOSFET, in the future, what we're gonna do is that we're gonna look at VGS is the input and VDS is the output. So on the same circuit, you see what happened in the gate right now? We have this two voltage source. We have two voltage source. And we know that because we use it as an amplifier, so this circuit is actually in linear operation. So in linear operation, we should be able to use superposition. So ideally, you would solve DC and then AC. But there's one trick, because when you do AC, you'll find, well, it's not going to work because the AC voltage is so small, it's not going to go to saturation mode. So that's where we have trouble to directly use the superposition. But the principle is the same. It is a superposition. So let me do this. We can draw the DC circuit. Let's start with the DC. So the DC. For the DC circuit, when we do superposition, when we do the DC, we simply short the other voltage source, right? So okay, so we get this one. So now we have this very simple DC circuit. So in this DC circuit, we can find out what this VD is. VD is equal to VDS. So VD equal to 1/2 K W over L. Well, in the book, okay, this is a little bit, I want to make sure that you guys have this same with what it's in the book. In the book, what they did is this. They did this K M plus L equal to K. So instead of using KWL, they will replace it with a simple just 1K, just to make it simple. Nothing have really changed. The principle is the same. So here we're going to use K times VGS minus VT squared. Sorry. Okay, mistake again. So basically, we're going to say VD, oops. So VD equal to VDD minus, oh, let's write again. So VD is VDD minus RD times ID. Oh, this is better. Okay. We got this one. So VD is VDD minus RD times ID, and ID, we got that equation over there. So that's what we get. And then instead of using superposition, what we're going to do is we're going to do a little bit different. So we're going to do the combined circuit. So this is for VDC. Let me change a different color so that. So this one, we're going to do this circuit over here. So what's this circuit? If you remember, the top equation is the ID 1/2 K times VGS minus VT, but now VGS has two components now. It's a VT is a DC VGS, it's also small signal, the AC VGS. So we're gonna do, I think what they call is this VD, the capital VD equal to VDD minus RD times ID, but this ID is now VDD minus RD times, this ID is going to be, well, let's write ID here too. So this ID is like lowercase ID. So this ID now is equal to 1/2 K times VGS plus VGS minus VT squared. So you got this one. So on the previous, on the red circuit, you have the ID is VGS minus VT, but on the lowercase, on the blue circuit, you have VGS minus VGS plus VGS minus VT. So you can see there's a little different. So what I'm going to do is I'm going to expand this equation over here. I'm going to expand this into VGS minus VT plus VGS lowercase squared. I'm going to expand this again to K times VGS minus VT squared plus 2 times VGS minus VT times VGS, and then plus VGS squared. This is a very critical step. So we expanded the quadratic equation into 3 terms. If you look at inside the bracket, there are 3 terms. The middle term is the one that is important. The last term over here, we're going to neglect it. We're going to just say, we're going to cross this one out. Do you know why? Because VGS is supposed to be small. And it's so small that when you take the square of that thing, it becomes even smaller. So typically, the ratio between this VGS and this VGS is at least like 10 to 100 times. So which means this like 0.1 times of, that's maximum, sometimes 0.01. So let's assume this is only 1 times of VGS. By taking the square, what do you get? It's like 1%, right? So it's really small. So we're going to take off this one. So if we take off that one, so we're going to do this. We're just going to get that. So now we're going to plug in this one into this equation over here. Then we're going to plug this equation into, to this equation over here. So we are going to get, then we're going to get V lowercase VD equal to VD capital case VD minus capital case VD. When we minus this one, use this one minus, when you also you plug in this one to here. You see this VDD is the same, right? So they cancel. And then when they cancel, like there's a minus sign here, right? And then also there's 2, and this 2 would cancel too. So this K comes inside here. You just see this term is same as the top equation there. And so those are going to cancel. So this one, when you minus this one, this is going to cancel. So what we'll get is only the second term, which is K times RD. So this is what we get from the there's also VGS. Sorry, that's what I meant. Lowercase VGS. So this is what we get for the output for the difference between the DC and between the total AC plus DC and then the DC. So so think about it. So initially you have something. Now you added something. So the difference of the response is the result of that little disturbance, right? So maybe in real life, if I could think of example, or let's say you go buy something in Costco, or not Costco. Costco is not a good, Ruff's, for example, and you buy $19 of worth of product, but you saw a coupon says you will get $5 off if you buy $20. What would you do? I would buy another something for $1, then I got $5 back. I still pay, less than 19, right? So you see that $1 that you put give you how much back? Well, $5 off, you got at least, you spend $1 more, you got $4, you got $5 back. So you still earn $4. So the other $1 resulting in $4 of income. So similarly, for the circuit like this, you got the DC circuit, it's working fine, but it doesn't do anything for us. We want to use it as an amplifier. So we add a little small signal on top of that DC. At the output, we're going to get something. So that something is a result of that little input. And it's called amplifier because output is always bigger. Well, not always. Sometimes for the common emitter, it will be smaller, but most of the time it will be bigger than the input. So if we input, let's say, is 1 millivolt, the output is 100. So you got 100 times the gain. So that gain is expressed as little VD over little VGS equal to, just simply move everything from this side, from this one to the other side, you got this. So you got this K times VGS minus VT times RD. That's your gain. That's your gain, right? But RD is something RD is something that does not belong to the MOSFET itself. It's external to the MOSFET. So most of the time we'll leave the ID out. We'll give something in the middle here. We'll give it a name. Okay, and this thing is called we call this GM. Well, we call it GM because G stands in circuit, R stands for this like a resistance, and you also have conductance. But here you see something times RD has a constant. So GM we call it like it's like a little gain to the circuit. Okay, so we're gonna get GM to K times VGS minus VT. So by this time, you will be able to, let's write it down. So VDS equal to GM VGS. So what it really means that if I redraw the MOSFET, remember how the MOSFET is like this. And this is where we put the VGS, and that's where we put the ground. This is VDS. So for the whole MOSFET circuit, what you see is that VDS is proportional to GM times VGS. And remember, there's no current going in to the gate, no current going into the gate. So in that case, what we really get is we can draw the equivalent circuit now because the output is like a is a controlled voltage source, so that we will have VGS coming in, and then no current going through that circuit. So this is the source, and here, so we have no, I think I made a mistake. GM times VGS. No. So this has to be like times RD, and this gives you VDS. Okay. Let's see what do we have. I think somewhere here in the previous slide, I made a mistake. Why is this? Okay, let's see what's happened here. So we got VD equal to VD minus VD equals K times RD times VGS. And then we got VGS on the other side, we got K times RD. And we got GM to RD. Oh, that's why. So with GM, we need to rewrite this one. So VD is equal to GM times RD times VGS. Okay. That's right. Okay. So VDS times RD. So that's what I was missing. So GM times RD times VGS. So because this is written like this way, we probably can write down as VDS equal to because VGS is input. So we want to say is GM VGS times RD. And this one, do you see what happens? Also, I think I missed the minus sign. Yeah, sorry, this has been a long time. So there's a minus sign that I forgot. There's a minus sign. Because when you minus, this quality becomes minus because the RD has a minus in front of it. So we get a minus, okay? So this one, we have minus and minus, okay. So you see, that's this is important because this RD is resistance. Then resistance times something to get voltage. So this something must be a current. So GM times VGS becomes the current. So that's why we have a current source that's plotted over here, or it's something over here. And the VGS input is coming in, and your output is VDS, because this is the ground. So you see here in this circuit, so VGS coming this way, I mean, GM times VGS comes this way, it comes this way. So if you still have a doubt, you can use VDS minus 0 equal to RD times this current over here is GM times VGS, right? So VDS minus 0 equal to, well, the current goes up. So this has to be the other way around. This has to go from 0 minus VDS because current goes from here to up. So 0 minus this voltage gives RD times the current source. Those exactly gives you what we have. So that's how, and then because RD is external to the MOSFET. So therefore, when we draw the MOSFET equivalent circuit, we can remove the RD, which basically becomes that circuit over here. So which means that circuit is equivalent to this MOSFET. So this is MOSFET. source, drain, and gate. Okay, so this one is the top one is the equivalent circuit of the bottom one. You got the source here and the source here. You got gate coming in, no current. Even though on the MOSFET it looks like one, but on the top you have the gate drain on the other side. So that's what you have for the. So this is very important because let me do one thing. So the next one is looking at this is really tough. Okay. So sometimes, remember in the early, we talk about the RO is when the MOSFET is non-ideal, you got this RO equal to VA early voltage divided by ID. And then that RO in the DC circuit, we already know that it's in parallel with the current source. So therefore, that RO is part of the MOSFET. So the blue part inside the circuit is a part of the overall circuit. So that VA divided by ID, that gives you the internal resistance. So if you have RO, now the output is going to be slightly different. So because this VDS is going to be GM times VGS minus times RO in parallel with RD. See now RO and RD are in parallel, right? So therefore the voltage is different than it was before on the previous slide, because the previous slide assumes it's ideal. MOSFET, there's no RO, now you have RO. So tell me, with RO, your output is smaller or bigger? Big or small? Bigger? Why? Hmm? No. The voltage source, you see the voltage, the current source, GM times VGS. So VGS is given, GM is constant. So GM times VGS is the input, VGS is input. So that is given. When VGS is given, that current source is given, control current source is given. When you have RO, you got RO and RD in parallel. When two resistors in parallel, it's always smaller. It's always smaller than each of the resistance. But the good thing is that RO is usually much bigger than RD. Like RD is 10, RO maybe 100. Therefore, when these two in parallel, they do reduce a little bit, but not so much. So let's do one more example. We're probably going to be able to. Okay. This is a circuit you're going to see a lot. You're going to see a lot in amplifiers. We add capacitors. Can you tell me what happens with a capacitor with a very high frequency AC connected? Yes. It passes. Why does it passes? No. Yeah, it's fast, but why? Why would it pass the AC? Hmm? Yes. Huh? No. So remember the impedance of XC. How do you write the impedance for XC? Is it 1 over omega C? 1 Well, G, of course, you GC, G, you know. So when omega is big, what happens? Zero. When omega is very big, when X is close to zero. So if a voltage source connect to something like a impedance which has a zero impedance, it passes. Right? What happens if we connect something to some DC voltage to a capacitor? What happens? It blocks it. It's not going to go through. So in the future, you're going to see a lot of circuit like this where you have a capacitor. So in this circuit, for example, if we look at the DC circuit, if we look at the DC biasing, we call it again biasing. What happens to that RG? Well, I mean that VI. What happens to VI for DC? The capacitor is going to isolate it, so it has nothing to do with the DC. How about RL for DC? It's nothing because it's isolated. It's open. The C is open for DC. So C is short for AC, but it's in this particular class, it's short for AC. But if the frequency is not right, it's not going to short, right? We are always assume the frequency is so high, the capacity is so big that it's going to short, and it's going to open for DC. So let's look at the DC biasing. Because we said there's nothing to do. This is the DC circuit. See, in this one, right away you can say, oh, wow, this is a very simple circuit. That was so complex, but now it's so simple. So in here, we can easily calculate, for example, ID. We can simply calculate ID equal to, again, 1/2 K times VGS minus VT squared. And then we can calculate IVD equal to VDD minus ID times 10K. So the only thing you have to be careful is how to calculate VGS. And some student telling me VGS 0, because they said, well, this is connected to 0 and this is connected here. VGS 0. Do you believe him? No, why not? Is VGS 0? Well, it's not connected to ground, so why would it be 0? It can't be 0. It's not connected. Well, it is connected here. But remember, there's no current here. No current here, no current. So if there's no current flowing from the through the capacitor, what happens between the two ends of the resistor? What happens to the two? Zero, right? The voltage difference 0, which means the voltage here and here is the same. So in this example, your VDS is the same as VGS. Okay, so your VDS is the same as VGS. You can plug in this VGS into the above equation. You can use to calculate how much that ID is, how much that VD is. We're not going to go through the math. But then, once we have done that, we need to come back to AC. Okay, so this is a DC biasing. All right, a little bit, but this is basically the same circuit over there. Okay, so what for the AC? As we said, the capacitor becomes 0. So this VI. What happens to the, so this resistor over here. So this is the actual circuit, right? So this is the actual circuit. This is the input. We just simply remove the capacitor here. We remove the capacitor over here. So this becomes AC circuit. For this AC circuit, how do we, if we replace this MOSFET with the equivalent circuit of small signal, do you still remember the equivalent circuit for the small signal? It's like this. Without CM. So without any RO, you got this. So what we would do is we will put this one to replace this. You will get the small signal equivalent circuit. So this is what you would get once you have RO. But the only thing to remember is that there's a resistor between that G, the gate, and the drain. So if you don't have that, it will be open circuit between G and D. But since there's a resistor, so now you have something connected here. So once you have this circuit, you can simply do a nodal analysis. Nodal analysis, right? You have how many nodes do you have in this circuit? It's one node, right? There's a super node over here. So you can do, let's say this one is VO. So this is VO, which is given here, VO. So VO, all VO. So you have VO minus VI divided by RG, which is the current going this direction, plus current going this direction, and this direction. And that's three resistance, they're all in parallel, right? So we basically can really, to simplify the circuit, we have simplified all the three in parallel to become RL prime. So RL prime equal to RD, so RO in parallel with R, which is the one? RD and RL. So now you have this VO divided by RL prime. This is the current coming out this way, and you have current coming this way. So plus GM times VGS equal to 0. So with this equation, you can solve for VI. So that's very simple. Okay. So we're going to stop here because we're going to take the quiz. Let me quit this. Yeah, quiz are open notes. Huh? Yeah. You guys have a